Welcome in Carodor. Today we are going to discuss Chapter 2. We learn Chapter 2 about sound. Let's start. Here, as you see, we have here the tuning fork and these longitudinal waves coming out from it to reach our ear. So sound and tones are produced due to the vibration of objects. We have here a tuning fork. This tuning fork, as you see, it makes a vibrations. Look, yes, this vibration makes a longitudinal sound to reach the ear. Then the ear transmitted this sound to the, of course, to the brain, and the brain, of course, yes, and the brain after that translates them into sounds. After that, we have here the first characteristic for the sound, which is the reflection of sound. Here in reflection of sound, as you see here, yes, sound hits and reflects again. We can see it again. Concentrate well. Yes, look, and reflects. So what's meant by sound reflection? Sound reflection is the restoration or returning back or bouncing of sound waves. Is restoration, returning back or bouncing of sound waves to the same medium when it meets a large surface. As you see, this large surface, this a source of sound, and the sound is reflected by this way. The sound is reflected by this way. When a loud sound is produced at a suitable distance from a wall or a mountain, a sound is heard. A sound is heard back, looks like the original one, and it is the meaning of echo. When I call someone or I say Ahmad, Ahmad, Hamad, Hamad, this is an echo. So echo, it is a repetition of sound due to its reflection. It is echo. Echo means the repetition of sound due to its reflection, And sound waves propagate in air in the form of concentric spheres of successive compressions, rarefactions, compressions, rarefactions, compressions, rarefactions, and so on. It is a way of propagating sound in air. It is a way of propagating sound in air. And of course, the center of sound, the center of this source of sound is the source of sound. The center of these waves, is the source of sound. Okay. After that, if we have here, yes, a mountain, and here the source, and here the human ear. Of course, the source of sound makes these waves falling on a large reflecting surface, a big reflecting surface such as a mountain, then it reflected again to reach the ear. And the distance mustn't be less than 17 meters. Mustn't be less than 17 meters. So if these waves are obstructed by a large obstacle, they are reflected back in the form of concentric spheres of compressions and rarefactions. So sound ray here is the straight line indicating the direction of propagation, of the sound waves. And we can conclude the two laws of sound reflection. What are the two laws of sound reflection? The first law, angle of incidence equals angle of reflection. Angle of incidence equals angle of reflection. This is the first law. What's about the second law? The second law, the incident sound ray and the reflected sound ray and the normal all lie in one plane. This plane is perpendicular. This plane is perpendicular on the reflecting surface. I repeat it again. Incident sound ray, reflected sound ray, and the normal line at the point of incidence on the reflecting surface all lie in one plane. This plane is perpendicular on the reflecting surface. These are the two laws of sound reflection. So, angle of incidence equals angle of reflection. This is the first law. The second law, incident sound ray, reflected sound ray, and the normal all lie in one plane. This plane is perpendicular to the reflecting surface. That's for these points. What's about refraction of sound? Sound refraction. Sound refraction means the change in the direction of sound. when these sound waves passes, transfers, transmits from one medium to another. When sound transfers from one medium to another, of course sound will be refracted, that change in the direction. So sound refraction is the change in the direction of sound propagation. Okay, so how can the sound waves can be changed in its direction? How? You have first to think about why the direction is changed. When I speak, sound here moves in the same medium. When it moves in the same medium, so sound is not refracted. The direction is not changed. But when my waves transmit from air to another medium, which is water, of course it will be refracted. Why? Due to the change in the velocity. Due to the change of velocity. Does the velocity of sound in air equals the velocity of sound in water? Of course not. Of course not. The velocity of sound in air is less than the velocity of sound in water. The velocity of sound in solids is greater than the velocity of sound in water, is greater than the velocity of sound in gases. That's for all types of medium. But what's about in gases? What's about in gases? You have to know the velocity of sound is inversely proportional with the square root of density of gases. How? If you have a gas with more density, with greater density, so the velocity will be, very small. Greater density, the velocity of sound in this medium will be very small. Greater density such as carbon dioxide gas. But what's about this hydrogen gas? Hydrogen gas has a less density, has a small density if it is compared to carbon dioxide gas. So here small density means higher velocity. So sound reflection. Sound reflection is the change of the direction of sound propagation when it transfers from one medium to another. The velocity of sound in each medium is different. And we can summarize our definition in another word, in another relation, in another very important relation, which is sine phi divided sine theta equals V1 over V2. Sine phi divided sine theta equals V1 over V2. Phi means angle of incidence. Theta equals angle of refraction. V1, the velocity of sound in the first medium. V2, the velocity of sound in the second medium. So sine phi divided sine theta equals V1 over V2. So when the velocity of sound in the first medium is V1, is greater than the velocity of sound in the second medium V2. So the sound refracts, nearer to the normal. When sound moves from higher velocity, from a medium of higher velocity to another medium of lower velocity, so it moves like this and refracts near to the normal, towards the normal. But the opposite is correct. The vice versa is correct. When sound moves from lower velocity, such as carbon dioxide, to another medium, which is hydrogen, which is higher velocity, from lower velocity to higher velocity, so it refracts away from the, this is the normal, so it refracts away from the normal. Okay, so please don't forget this relation, V1 over V2 equals sine phi divided sine theta. Phi is the angle of incidence, theta is the angle of refraction. V1 the velocity of sound in the first medium, V2 the velocity of sound in the second medium. Okay, so we have here a person under water surface doesn't hear clearly that sound produced from air because there is a large difference in velocities. So this large difference in velocities between the two media, and most of the sound energy reflected, and just a small part enters the water. When I am when I'm standing beside a swimming pool and another one is swimming in the swimming pool. Okay, so when I speak to him, a little of sound reaches to him. Why? Because most of sound energy coming from me, is reflected from the water surface, and small part, just a small part, enters to the second medium. And due to the large difference in velocities, the velocity of sound in water is greater than the velocity of sound in air. So because there is a large difference in velocities between the two media, and most of the sound energy reflects at the water surface, and small part of sound energy enters the water. Finally, please don't forget the relation between the velocity of sound in gases and its density is inversely proportional with the root of density. At the end, I hope to understood our points for today for sound reflection and sound refraction. I hope to join us in the next parts. Thank you and goodbye.